Hi, Lokush. Lokush, okay. So the last homework, as I said, I included maybe the second question I intended to be like a little more challenging, and it seemed like maybe for some people it was, but I think it was a fun question, so hopefully we'll get to talk through and appreciate it. But yeah, starting with the question one. So question one, I think this is something someone asked about, like what happens to the unions of hypothesis classes, and then it's sort of a more general result that one can prove, but this is a special case where we had two hypothesis classes, H1 and H2, and we assumed that each of them had VC dimension at most D. And then we wanted to show that the VC dimension of their union is at most 2D plus 1. So yeah, there are like a couple of approaches to this. You can try to do it directly too, but I think Jean-Marie had a nice approach. It's very concise. So if you could talk us through that.
Of course. So basically, in order to show the inequality, we need to show that it is impossible to shatter a set of 2D plus 2 elements. And of course, this will also imply that you cannot shatter a larger set, because shattering a larger set also contains a shattering of a smaller, of all of its subsets. And in order to show that a set of size 2D plus 2 is not shattered by H1 union H2, we simply count the function or the possible hypothesis on 2D plus 2 elements. And if 2D plus 2 elements are shattered, you need 2 to the power 2D plus 2 functions. And we can use Sauer's lemma to show that you don't have enough function in H1 union H2.
Mm-hmm.
So if we simply write the statement of Sauer's lemma for sets of size 2D, of size D, I guess. Yes. For a set of 2D plus 2 elements. And we get the sum for I from
I guess H1 restricted to C. It's but yes, I was that's equal to sum of
for I from 0 to D of 2D plus 2 choose I. And now we observe that this is also equal, just by a property of the binomial coefficient, to the sum from I equals 0 to D of 2D plus 2 choose 2D plus 2 minus I. And so we observe that this is both H1 and H2 restricted to C, which have this property. So the cardinality of H1 plus union H2 restricted to C is smaller or equal to the first expression plus the second. And now if you observe those two expressions, you will see that it's exactly the development as a binomial formula of 2 to the d plus 2 with one term missing. And basically it's the term in the middle of the binomial coefficient development, which is, yes, 2d plus choose d plus 1. And because this last term is it's larger than 0, then the what we needed to prove follows.
Right. So basically, we get that there are fewer functions in the restriction than we would need in order to shatter the whole set, and it cannot be. I guess maybe I can just write down one specific example, just maybe in the abstract it's a little obscure. Let's say d is equal to 3, and then if we assume we can shatter something like 2 times d plus 1, which is 8. Then what we get by Zauer's lemma is that we get is like 8 choose 0 plus 8 choose 1 plus 8 choose 2 plus 8 choose 3. And we get this twice, so we get it for H1 restricted to C, HJ for J equals 2. But then, as Jean-Marie said, we can, this is actually also equal to H choose 8 plus H choose 7 plus H choose 6 plus H choose 5. So if we add these two up, then we get all the binomial coefficients except for so we get it for the sum of all of them minus the middle one, which is 4. And then this one is 2 to the 8. So that's why we're basically short on the yeah, I think you can use this approach to put some bounds even if you start out with different dimensions, but I think I'm not sure if you can say
it's
maybe
just a different
it's
coefficient that is missing in the sum,
right,
I guess.
Yeah, so I guess in general for two of them you can always say that the VC dimension is less than the sum of them plus 1. And then if you have more than 2, then you have to be a little more careful when the bound that you get is a little different. Okay. Does this make sense? Any questions?
No, it's very helpful. Thank you.
Maybe for the intuition, you can imagine that one set of hypotheses is all the elements, all the functions that have at most some number of 1, and the others are all the functions that have at most some number of 0, and you see that the inequality is tight. in this way.
Hmm.
Is this also true? So this is in the case that y is just two elements, but is there something which we can say when y is bigger?
It probably gets trickier. I think there's, I mean, first of all, yeah, I guess we didn't define the, so the VC dimension specifically is defined for binary classification, and there's an analog of it, which is defined for more general classification. And I think it's called, it has a name, it's called maybe Nagarjan dimension. I don't remember. Maybe. Yeah, but then yeah, probably the showing a bound in terms of yeah, for the union is, I think it's probably some more complicated expression. It could be worth looking into. I don't know. I don't know what it looks like off the top of my head. Even for the VC dimension, if you try to do more than two classes here, it gets a little trickier. But you can definitely find these bounds. Okay, so maybe can move on to question 2. So this is an example where we're looking at a specific hypothesis class of conjunctions over a Boolean algebra, and then I guess it's an interesting question because we saw early on that for finite hypothesis classes we can bound the VC dimension by the log of the size of the hypothesis class, but here we can actually compute the VC dimension. It turns out to be something strictly smaller than the log of the size. So let's try to work this out. So the setup was we have a set D, and then we take our domain to be just binary evaluations over D. And then our hypothesis class was of this form where we take conjunctions of some variables along with the conjunction of negation of some variables for some subsets. And then part 1 was just showing that the size of this is less or equal to 3 to the D plus 1. Yeah, Ohad, could you walk us through the solution?
Yeah. So for the first part, first of all, I exclude the special conjunction that forms a contradiction, because if I and j are not disjoint, then the resulting function always gives false. So yeah, that's a special function. But other than that, I claim that I and j can be uniquely constructed from a given conjunction. That is, if we have phi as a Boolean function, then we can find I and j from it, and they do that by defining I to be the set of all indices, such that the proposition is proposition and the negation of xi is a contradiction.
So these are the indices such that
Yeah.
phi
phi x and not xi is always 0.
phi of x and phi of not x are both 0.
No, I mean for phi of x and only the literal, and the negation of the literal xi.
This equals 0.
Yeah, and an alternative way to say this is that phi of x always implies xi.
Right there.
And now, so we prove a two-sided inclusion. If the index I is in the original set, then this is easy to see because xi appears as one of the terms in the conjunction. But on the other hand, we can show that any I that satisfies this implication must be in the original set. And we can show it by showing the contrapositive. For every index I, not in the index,
Right, so
not
so
in
one
the
second.
big I. We showed it doesn't apply.
Sorry, I'm a little lost on what we're proving now. We're just trying to prove that for any classifier phi, if it comes from such a conjunction, then that conjunction is unique. Is that what you're
Yeah, and okay, actually, maybe showing the uniqueness isn't necessary for this part. It just
right? Because I guess we're just trying to show it's less equal. But I guess it's it turns out it is take maybe we can, just for the sake of time, take it a little briefer.
Yeah, so we can define a function from age to the set d to the 3, which basically means splitting all indices into 3 disjoint subsets, and the 3 subsets we choose is I, j, and d minus I union j.
It's like so a bit. Okay.
Yeah, so you could say like elements of I match with 1, elements of j match to 2, and other elements match to 3. And yeah, we can show that once we exclude the zero proposition, the contradiction, then this function is well defined because I and J are always disjoint, and it's also injective. Yeah, it's injective because I and J uniquely define phi. Yeah, so this shows that the size of H minus 1 is at most d to the 3. So it's a 3 to the power 3.
Right.
Mm,
Yeah, that makes sense.
okay, so for now, there's the first bound on the dimension. So we always know that the dimension of H is at most log 2 of the size of H. So that means we can bound the dimension by log 2 of 3 to the d plus 1. Yeah, and we actually want to show something a bit stronger. We want to show that it's less than or equal to log 2 to the to 3 to the d. So we need to show somehow by taking the flow of this. We can't have it exactly be the plus 1. Yeah, so see here I wrote like I wrote k equals, yeah, okay, so that's what we want to show, and this follows from number theory. Yeah, the 3 to the d here is 0 mod 8. Wait, okay, 2 to the k is 0 mod 8. But the powers of 3 are only 1 or 3 modulate, so it never matters. Yeah, and we only have the solutions where d equals 0 and 1. These form powers of 2, but after that it never happens.
How do you get the 3 to the d is 1 or 3 mod 8?
So we know that 3 squared is 9, which is 1 modulo 8, and then if we look at the orbit of 3, it's always 3 or 1 because it's 3. Once we multiply it by 3, it goes to 1.
Wow.
Then when we multiply it, it goes to 3 again. So it's a periodic path.
Wow. Cool.
Yeah, we can also say that the subgroup of the subgroup generated by 3 modulo 8 is just these two numbers. Yeah, so that solves part 1. Okay, so they continue to part 2.
Yeah, maybe let's pause for a sec if anyone else has any question. Okay, so yeah, maybe we can start with part 2. And part 2, we wanted to show that the VC dimension is actually exactly equal to the size of D.
Yeah, and here we saw that D is both a lower bound and an upper bound. To show a lower bound, we want to construct an explicit set C of size D that is shattered by the hypothesis class, and I constructed the propositions the valuations E1 up to ED. EI are all functions from D to 0, 1. And the EI is the assignment that sends I to 1 and the others to 0.
Mhm.
Yeah. And now we claim that the set of hypotheses is restricted to C is exactly the set of all functions from Z to 0, 1, which means that given a general function f from C to 0, 1, we need to construct an explicit conjunction that matches all of these elements. So given this f, I define J to be all indices such that f of EJ is false, or EVJ in this notation. And I define the conjunction to be phi equals to the conjunction of not xj for all such j. And now we want to show that the restriction of phi to C is exactly the function f, which is basically true by definition, because if for every j that should be false, we explicitly making it false by taking the one variable that is 1 in EVJ and explicitly demanding it to be 0. Yeah. Yeah, and this shows the first dot. This shows a shattered set of size D.
Mhm.
And now in the other direction, I started by taking a shattered set of size at least D plus 1 and construct a contradiction. So yeah, I'll say that the size of it is M, and that M is at least D plus 1.
Mhm.
Yeah, so I write out explicitly the elements of C as V1 up to Vm, where each Vi is, I think of it as an assignment. It's a function from D to 0, 1 that says for each variable xi if it's true or false. Yeah, and now I define M functions from C to 0, 1 by ft sends everything to 1 except our selected element. Okay, the indices are a bit confusing. Yeah, okay, that's basically that's it. So this function is true on the all assignments except one, which we diagonalized, and by assumption there is an explicit conjunction phi-c, which reduces to fc. Okay, and now I define M sets A1 up to AM, which I claim will all be subsets of D, and are all disjoint, and all of them are non-empty. And this will be a contradiction. And yeah, the explicit definition is the set of all right. So the set of all indices that appear in phi t in phi c, such that the corresponding literal is it doesn't hold for VC. And explicitly, it means, yeah, all I in I, such that VC of I is 0. Or J in J, such that C of J is 1. Okay, so now we claim that AC is always non-empty, which is because the proposition C is 0 on VC, which means that it's not a tautology. It's always false on at least one element. So either I is non-empty or J is non-empty. Yeah, and for the second part, yeah, here the notation gets a bit complicated. So I just proved it for A1 intersection A2, which holds without loss of generality. Okay, so yeah, I'll go through the proof with assuming that it's A1 and A2, but you can match it to be more general. So since A is in A1, then it appears in the corresponding proposition phi1, either in positive or negative form. I assume without loss of generality that it appears in a positive form. That is, the proposition C includes XA as one of its conditions. By definition of AC, it means that
maybe we can say why this can be assumed without loss of generality.
Yeah, there's a symmetry here between positive and then negative literals. If it was the negative literal, then I'll think I switch all assignments, like switching between 0 and 1 in the assignment of the variables themselves. Yeah, I didn't exactly formalize that, but I do think that the other direction, like working with JC, will be basically the same. Yeah, so unfortunately, at this point, the notation between my answer and this one get a bit different. So it's hard for me to reconstruct the exact argument. But I claim that, like, by definition of AC, the corresponding assignment is 0 on this variable. But phi of v2 is 1. Because of the definition, and since xa is one of the terms in the entire conjunction is true, it also means that yeah, okay, so yeah, that's basically it. Now we also have that A is in the second set in either positive or negative form. I claim that by what we saw here, it must appear in negative form, otherwise it contradicts. And then, okay, and now because the number of because D is at least 2, the number of elements is at least 3. So we can look at a different assignment in C that is different from both C and gamma. Now, I claim that this X has no valid value for the variable A. Because if let's see. I claim that if it says 0 in that, then since the first conjunction has it in a positive form, then it results in 0. And if it's 1, then if it equals to 1, then the second conjunction is false on it. And in any case, we found out that one of the original 2 conjunctions, phi1 or phi2, is always false on this third variable. And this contradicts the way we constructed this phi.
So this part contradicts this.
Yeah, and because of this contradiction, the number of elements can't be larger than D.
Right, I guess maybe to go back here, we have these subsets, one for each element of C. Each is non-empty and disjoint from the others. So it's impossible to have D plus one of those by the pigeonhole principle.
And then what is the function C again?
So C was for anything in the in our set C. So I guess C is both C and gamma are in C, and then these are this is a subset of X. which was 2 to the d.
And so what is this AC really? What's the intuition?
Yeah, my intuition was that we take the original set to be a set of a lot of assignments, and we assume that any function from these assignments to true false is realizable by some conjunction. So the the functions I choose that are hard to reconstruct are the functions that that are true for all assignments except for one. And then like I dig into the structure of each assignment, and I conclude that there must be at least one literal inside this assignment that is false only for these assignments and for no other assignment. So we have an index that is special for this assignment, sort of. But we have more assignments than the number of variables, so it somehow doesn't make sense.
Got it. Got it. So you're looking at this function from C to Y, and then you say, okay, take any of these, take any one of these mappings from C to Y, and you can show, well, it has to have a certain structural element. It has to have a certain structural property in terms of the set I and J that defines the hypothesis, which is, and these sets are like much smaller in a certain way, much less expressive than the full 2 to the n set of possible truth tables. Because we're dealing with this not general propositional sentences, we're dealing with only conjunctions and negations. Oh. Is that roughly accurate?
Yeah, I constructed so that almost all conjunctions are true, and if a conjunction is true, it means that all variables inside these conjunctions are true. So, but by each assignment, almost all variables become true, except for a small set of special variables that that is mapped specifically for our one specified assignment. Yeah, that's my intuition. Maybe there's a more clear way to look at this.
And so then, Gerge, why is AC 3 in this case?
Yeah, so basically the way AC was picked out in Ohad's solution is that, so we look at the literals that appear in the corresponding phi C, and then we chose phi C so that phi C of C is false. So that means at least one of those has to be evaluating to false, and in this case it's just the third one, because the third one is 0, and then the other two are in this example true. So we pick the one that makes C false in that case.
Got it. Got it.
And then there has to be at least one of those, because we constructed in phi C in a way to make C false. And then yes, as we talked through, it's a little takes a bit of looking through it carefully, but you can show that they also need to be disjoint given the construction.
Amazing. Cool. Thank you. Thank you both.
Yeah, thanks, Alan. Okay, so maybe, yeah, are there any other questions about this? yeah, I think most people who got a solution, they use some form of pigeonhole principle like this. Basically, the idea is you cannot squeeze in enough of these that because of the limitation in the size of D. But I think this is a particularly clean way of saying that by defining this A subset C, A sub C, which are the things that make a specific one false, and show that these need to be disjoint from each other. Right. So if there are no more questions, I'll stop the recording here.